Mario finds a pipe that leads to an underground room where everything is made of concrete. He finds a small sleeping thwomp of 50 kilograms and needs to push it across a dry concrete floor with a force of 200 newtons until the thwomp meets the wall 15 meters away so he can escape the room. If the coefficient of kinetic friction is 0.75, how much does the thwomp heat up if it starts at 25 degrees Celsius? The specific heat of concrete is 880 joules per kilogram Celsius. Here's a free body diagram of the situation. We have the force of the push on the thwomp by Mario, which equals 200 newtons, the force of friction, which we need to find, the normal force, and the force of gravity, which cancel each other out, as we will find later. Then we have a more detailed schematic, aka the extended object model, with the wall, the concrete floor, and the thwomp, showing the distance that the system, the thwomp, travels, as well as the forces acting on it. So to start off, let's find the values of our forces in the free body diagram. F net in the y direction equals the normal force minus gravity, which equals 0 because they cancel each other out, being equal in magnitude. Since we know how to find Fg, we do the calculations to find that our normal force is 490 newtons. Later we can use our normal force to find the force of friction on the thwomp. But first, let's establish that since we're interested in the energy of our system, specifically thermal, because the velocity of the center of mass does not change throughout this entire scenario, delta K trans equals 0 here, and our energy equation is simplified to delta E thermal equals the work done by Mario's push and the work of friction. We can simplify our equation by saying that the change in thermal energy is equal to force times distance, that's the work done by the push, minus the force times effective distance, which is the actual distance on which the frictional force acts. For identical blocks, all atoms move the same distance d in the top object, the thwomp, but the lower contact, the floor, doesn't move due to the stick-slip contact between the two objects. And so the friction force, F here, acts only for a portion of the displacement, which equals d over 2 for identical blocks. So another way to write this is F over 2 times d, and F is the force of friction. Then we plug in our knowns. Work done by the push is 200 N times 15 meters, and we subtract from that the work done by friction, which is the coefficient of kinetic friction times normal force times 15 meters, all divided by 2 because of what we said earlier about effective distance. Ultimately, we get that our change in thermal energy is 243.75 joules. Change in thermal energy equals the amount of heat lost to the environment through friction. And by definition, Q equals MCAT, so we plug in what we know on both sides of the equation to solve for the final temperature of the thwomp. On the left, our change in thermal energy is 243.75 joules, as we just found, and MCAT equals 50 times the specific heat of concrete, 880, times the final temp, minus 25 degrees Celsius. Doing all of the algebra, we find that the final temperature is 25.0055 degrees Celsius. So we see that the thwomp heated up 0.0055 degrees Celsius due to friction, which is a very small amount.